Now we state an important theorem, and we prove this theorem, about open and closed sets. Before we do that, I don't think I gave any examples of open sets in the previous video. So let's take a look at some open sets. We're probably all not surprised that an open interval is an open set. Why is this an open set? Well, by the definition, choose any number in here. Choose x inside the interval from 0 to 10. I think rather than proving this, I'm simply going to say that let's choose 1. X equals 3.2. Well, 3.2, that's 0 on the number line, and that's 10 on the number line. 3.2, you can draw, this would be 3.2. This would be 3.2 plus epsilon. This would be 3.2 minus epsilon. You can get an epsilon small enough so that the entire interval from maybe I'll call it 3.2 plus or minus epsilon, that interval, is completely contained in this set right here. And even if you pick 9.99999, you can still find a really small epsilon such that 9.99999 plus or minus epsilon is still not touching 10. And one common way of coming up with that is just taking half of the distance from this to 10 and maybe make your epsilon equal to that. Okay, so open intervals are open sets. How about closed intervals? 1 to 5. Is this an open set? Well, we know it's closed, but we didn't say this earlier. A set can be both open and closed. Can be. Well, let's see, is this the case? Does any number in this interval have a neighborhood around it, an epsilon neighborhood around it, that is completely contained inside this interval? And the answer is no. The only problem points are the endpoints 1 and 5. 1, 5. This is like a closed interval. The number 5, though, if you go from 5 minus epsilon to 5 plus epsilon, beyond 5, in between 5 and 5 plus epsilon, is not completely contained inside here, no matter how small epsilon is. So this closed interval is not an open set. All right, how about R? Is R an open set? Well, of course it is. For every single number, you can find a neighborhood around it that's completely contained inside R. But R was closed also. So R is one of those sets that's both open and closed. All right, how about the empty set? This is vacuously true that it is an open set. Is there a number in, well, we could stop right there. Is there a number in the empty set? No, there isn't. You can't find a number in the empty set where a neighborhood does not fit inside the empty set. All I had to say was that there's no number in, we can't even do that test. So it's vacuously true that this is an open set. And if you remember, it was also closed. So R and the empty set are both open and closed. What we're going to prove now is a set E, subset of the reals, is closed if and only if R minus E is open. And in set theory class, we might call this R minus E is the complement of E, sometimes written like that. I'm not sure you can see that in the video. E complement is R minus E. So you could say that a set is closed if and only if its complement is open. And since it's an if and only if, you could say a set is open if and only if its complement is closed. All right, let's do this. It's a two-directional proof since we've got the if and only if. So we're going to start with the left-hand side. Let's see. We're going to assume that it's closed in order to prove that the complement is open. So how do I prove that something is open? We're assuming this is true. How do I prove this is open? Well, you start off by saying, give me a point in that set, R minus E. All right, well, notice if it's in the complement of E, X naught is not an accumulation point of E. How do I know that? Well, by definition, if E is closed, it contains all of its accumulation points. So if we're taking a point out of the complement, it could not possibly be an accumulation point of E. Maybe I'll take the period off there and I'll just say, since E is closed. All right, since it's not an accumulation point, thus, there exists, I'll use delta, greater than 0, such that X naught minus delta, X naught plus delta is completely contained in R minus E. Okay, well, why is this true? Because it's not an accumulation point. It's not an accumulation point. It contains an interval that contains, let me restate that. It contains a neighborhood around X naught such that there's no element from E in this set. If every delta, for every delta, X naught minus delta to X naught plus delta, contained a point of E, of R, which one? E, yeah. Then it would be an accumulation point, but it's not. So therefore, this is completely contained. We found the neighborhood of X naught. We call that a delta neighborhood that's completely contained in R minus E. Therefore, it's open. X naught, again, was chosen arbitrarily. So this would be true for every single point chosen from this set. That's the end of that direction of the proof. And basically, if we think of the closed set E as just being a closed interval, we chose a point outside of it, and we just found that since this is not an accumulation point for E, we can find an epsilon small enough or a delta small enough so that it's outside of E. Doesn't matter how close that point is to this interval, as long as it doesn't come into the interval, we can find that neighborhood. All right, the other direction. We're going to assume that R minus E is open, and we're going to prove that E is closed. Okay, if we want to prove that this is closed, let's let X naught be an accumulation point of E. And then we'll just prove that that accumulation point actually is in the set E. Let X naught be an accumulation point of E. And I'll write what I just said. We will show that X naught is in E. Therefore, it would mean E contains all of its accumulation points, and it would be closed. All right, well, let's do contradiction. To the contrary, suppose x is not in E, but in its complement, R minus E. Well, that means x in an open set. So, since R minus E is open, there exists a delta. I could use epsilon if I wanted to, but I'm going to reuse delta. There exists a delta greater than 0, such that x naught minus delta to x naught plus delta is completely contained in R minus E. I'm going to go ahead and say by definition of open set. And that's a contradiction. Since x naught is an accumulation point of the set E. Therefore, that contradiction means this is false. X is not in R minus E. So we have, since x is an accumulation point, x naught is actually in E, and E is closed. So not a long proof, but required both the definition of an open set and a closed set.